So the idea is to evolve towards a full-scale biorefinery through biomass depolymerization. What for? First, to produce low volume, high value chemical products, biosolvents, biopaints, and so on and so forth, and also to produce high volume but low value liquid transportation fuels. Remember, gasoline, fuel ethanol is a very cheap product. Also, there's a problem of enhancing sustainability of the overall operation. First, the energy balance in Brazil today is 9:1. That means you produce 9 units of renewable energy. To produce 9 units of renewable energy, you need 1 unit of fossil energy. This is quite good, but it's not enough because we know that fossil energies will disappear, so we have to do better. This is our Achilles heel, actually. Currently, our water balance is negative. We import a lot of water in the process. And if you do all the calculations, all the water needed in the process is in the sugarcane. And we still put more water in the process. And another very important problem is the soil nutrients recycling, because this operation currently in Brazil is not economical. These questions can be solved with that integrated agro-industrial model for the sustainable production and conversion of biomass into biofuels and added value products. That's why we're proposing this idea. This is the title of this speech, actually. Let's see what this model is. This picture here sketches what a typical sugar cane in Brazil is today. You have your plantation area, which has an average of 30 kilohectares, and corresponds to around-the-clock 500 tons of sugarcane per hour. This sugarcane is processed, mechanically processed. The straw can be separated and burned to generate energy. And then the chopped sugarcane is sent to the juice extraction process. This is where a lot of water is added. So you have juice, sugarcane juice, with a high sucrose content, and you have bagasse. The numbers here are around 130 tons per hour of bagasse, which is burned today to generate electricity. The juice can be used to produce sugar or ethanol. If you want to produce sugar, you send the juice to a cooking and crystallization process. Then the sucrose crystals are separated by a centrifugation operation, and you have a production of around 65 tons per hour of sugar. You also, in the centrifugation process, you have a production of molasses, which is also called sugarcane honey. It actually is it has a very high nutritional value. Sugarcane molasses is a very healthy product, and it's still fermentable. So you can, if you produce only sugar, you are able to produce a little bit of ethanol together with the sugar. I mean, if your unit is designed to produce only sugar, you're still going to have some ethanol being produced. If you want to produce ethanol, you send the juice to the fermentation processes, which can be pure or mixed with molasses. Here you have the production of 2 tons per hour of CO2, and then you're going to distill this wine to produce around 43 cubic meters per hour of ethanol. And here you have vinasse. And just to stress, this number, 50 megawatts, is the surplus of electricity. Okay, all the energy necessary here has been already taken into account. But what we are proposing to enhance efficiency and to enhance sustainability of these operations is to design a process that will depolymerize the sugar, the fermentable sugars contained in the cellulosic material by pre-treating and by hydrolyzation. Okay, so you're going to liberate fermentable sugars, which can be mixed to juice, to molasses, and you're going to be able to increase your ethanol production from 43 cubic meters to 82 cubic meters per hour. Okay, in the process, lignin is separated. It can be burned to generate electricity, or you can use it to produce some high-value chemicals. The other proposition is to recycle the nutrients contained in the vinasse and also the CO2 from fermentation through a photobioreactor, where you're going to cultivate microalgae in order to retain the nutrients, especially the nutrients contained in the vinasse and also the carbon from the CO2 from the fermentation process. So the steps here are the cultivation of microalgae, then you have a broth which is separated. The solid material is separated from the liquid material. Here you have clean or cleaner water. You also have nutrients, and you have some amount of lipids which can be converted to biodiesel, for instance, or it can be converted to some high-value chemicals. But for the sustainability, environmental sustainability of the process, in my opinion, recycling nutrients, it's much more important than producing, let's say, 1 cubic meter per ethanol of biodiesel from microalgae. In the process, you also, if you're producing biodiesel, you produce glycerin, which can still be burned to generate energy. But these propositions, as interesting as they might seem, they are not viable in the current technology status. One of the main problems regards sustainability. Let us revisit then our typical sugarcane industrial processing model. The area, as we have already seen, the average plantation area is 30 kilohectares, and the processing rate, the 24-hour processing rate is of 500 tons of sugarcane per hour. With this sugarcane, it is important to emphasize that you are carrying all nutrients that were absorbed from the ground. And these nutrients actually will end up mixed, diluted in the vinasse. When you look at the composition of the vinasse, you see nitrogen, phosphorus, potassium, and so on. And the corresponding mass flow rate of NPK is almost 1 ton, 975 kilograms per hour of NPK, just NPK. This actually is being carried out from the soil, and it must be taken back in order to assure sustainability of the operation. But the problem is that this amount of NPK is diluted in 499 tons of water, actually. There are several problems related to this practice. First, it is a highly uneconomical operation, since to apply 1 ton of NPK to the soil, it's necessary to transport and distribute nearly 500 tons of vinasse, as I already mentioned. Second, its high organic matter content implies a high biochemical oxygen demand, which can strongly impact the soil, groundwater, or nearby watercourses or lakes. Third, it is necessary to correct vinasse acidity. Its pH ranges from 3.7 to 4.4 in average. And it's also necessary to biodigest it to decrease the organic matter content in order to reduce impacts on soil microorganisms. Fourth, application of vinasse has a significant effect on soil mechanical properties, especially on the permeability, favoring soil compaction. Altogether, due to the fact that there are many types of vinasse and myriads of different soils, research results are still inconclusive or refer to particular situations, and application of vinasse as a procedure of fertilization/irrigation is still a debatable practice.